In our last part of section 2.5, we're going to do 2 more examples. They get a lot wordier, so when you look at them, you're going to see more words. But again, don't freak out because we're going to define those variables and write the equations just as we read them. So example 5 talks about the ideal gas law. It says the volume of gas varies inversely as the pressure and directly as the temperature. Temperature must be measured in kelvins to use this. If a certain gas occupies a volume of 1.3 liters at 300 Kelvin and a pressure of 18 newtons, find the volume at 340 Kelvin and a pressure of 24 newtons. So again, when you read that, you're kind of lost in everything, but let's break it down. Let's go define our variables first. So we need a volume. So I'm going to use V for volume of a certain gas. Pressure is the next thing they mentioned, so we use P for pressure. Whether you use uppercase or lowercase doesn't matter. And directly is the temperature, so we use T for temperature. And luckily they give it to us in kelvins already, so we don't need to worry about doing any conversions. In general, we won't have to do conversions with these guys. Okay, let's go write our equation. So the volume of the gas, V, is equal to K, and that's the varies. And it says inversely, so that means whatever goes underneath that is in the denominator, inversely as the pressure, so that goes down on the bottom. But then it switches gears and says, and directly is the temperature. So directly means it goes up next to K, so then we're going to put the T up top. So we end up with V is equal to KT all over P. So not quite in the order we expected it in, but we can still write that equation. Okay, if a gas occupies a volume of 1.3 liters at a temperature of 300 Kelvin, so I'm going to put 300 in for T, and a pressure of 18 newtons, so we're going to put 18 for P. And again, notice that for the most part, ignoring all the units, we're letting K take care of the unit conversions for us. Now we need to solve for K. So what I'm going to do is I'm going to come in and multiply both sides by 18 and then divide by 300. So we'll multiply by 18 and then divide by 300. And if you do that, so 1.3 times 18 and then divided by 300, you end up with a tiny k, not as small as the last one, but 0.078 is what you end up with. So now we have an equation that our volume is equal to 0.078 times T all over P. So now if you give me a T and a P, I can give you the volume, or give me 2 of the 3 and I'll give you the other one. And then wants to know, find the volume at 340 Kelvin and a pressure of 24 newtons. So we want to find the volume when the temperature is 340 Kelvin and the pressure is 24 newtons. And if I do that, so 0.078 times 340 divided by 24, I end up with 1.12. And because the initial volume is in liters, I know that this volume is also in liters. So, another variable thrown in there, but we were still able to work it with no difficulty. Okay, the last one I really like is a problem just because I think it fits Pueblo, where I'm located at. It talks about wind on a plane. So we can have some pretty strong wind gusts. And this one reminds me of that. So example 6 says the force exerted by the wind on a plane surface. So this would be like on the plane window, on the window of your car, the window of your house, on the house side, varies jointly with the area of the surface and the square of the velocity of the wind. And then it goes on to give you some numbers, but we need those variables first. So in example 6, let's come in and define some variables. So I'm going to let F stand for force. That's the force of the wind. We also need the area, so we'll use A for area of the surface. And then finally, the square of the velocity, so I'll use V for velocity, how fast the wind is blowing. Okay, now we can write our equation. So the force exerted, so F is equal to, okay, here it says jointly with the area, so that would be times A, and because it's jointly, we know to times again, the square of the velocity, so V squared. So I have F is equal to KAV squared. Wonderful. Then it goes on to tell me if the force on an area of 20 square feet is 11 pounds when the wind velocity is 22 miles an hour. Let's make sure we all pick that up. So the force is 20 square, I'm sorry, it says that the force on an area of 20 square feet, so this is 20 square feet, is 11 pounds when the velocity is 22 miles an hour. So make sure I get everything in the right spot. So 11 is equal to K times 20 times 22 squared. Okay, now I'll admit that I simply said, well, that means 11 is, K is equal to 11 divided by 20 times 22 squared. And then I just went directly to my calculator. So I didn't bother to calculate this out. I just divided it out. If you do that, K is equal to 0.0011. So now we have an equation that F is equal to that constant times the area times the velocity squared. So now if you give me an area, I can tell you what kind of force if I know how fast the wind is blowing. Okay, now let's backtrack just a little bit. This is saying a 22-mile-an-hour wind on an area of 20 square feet. So 20 square feet would be like a window that's 4 by 5 feet. So not a very big window. Well, I guess it is a big picture window. So 4 feet tall, 5 feet wide at the front of your house. The wind's blowing at 22 miles an hour. It's like 11 pounds of pressure. So it's like an 11-pound something sitting on that window, putting pressure on it. Okay, then it goes on to say, okay, find the force on a surface area of 47 square feet. So now we've got a different number, 47.125 square feet for my area, when the wind velocity is 36.5. So 36.5, we need to know the force. So that's what they're asking. Wow. So the wind is picked up. It's now blowing at 36 miles an hour. Sorry, yeah, 36.5 miles an hour. We've got a bigger window. It's 47.125. So 47.125, an even bigger window, 36.5 squared. And again, we're talking about a single pane window. Most windows are not just single panes anymore, they're double pane windows. Okay, so I put in the 47.125 for my area. I now have a wind blowing at 36.5 miles per hour. We're going to square that. We're going to number crunch this all through. And if you do that, it comes out to be 71.3. And then I have to backtrack and look and see what they measured the force in. You'll notice they measured the force in pounds. So if you have a huge window, 47 would be about like 6 by 8, right? 6 by 8 is 48. So 48 square foot, big window on the front of your house, but the wind's blowing at 36 miles an hour. Then this is like a 71-pound dog or person standing on that window, putting force on that window. So last December, we had those great big wind gusts and they were like 70 miles an hour. So imagine if this is 70 squared, how much force that's putting on that single pane window. So, and those are variation problems. Again, you'll see these crop up quite a bit in terms of physics and chemistry. They also happen over in the business world and econ economics courses. So you'll see them.